13.7 billion years ago, the universe existed as a single point with infinite density and temperature. Then it exploded outward. Astronomer Edwin Hubble first articulated this mechanism. His expanding universe hypothesis demonstrated that space itself is continuously stretching, increasing the distance between galaxies. This model directly challenged the prevailing steady-state concept developed by Fred Hoyle, which argued that the universe maintains a roughly constant size over time. The physics of the expansion moved rapidly. Within 3 minutes of the initial explosion, the first atomic nuclei began to form. Exactly 300,000 years later, the ambient temperature dropped to 4,500 Kelvin. Atomic matter solidified, and the universe finally became transparent. The resulting expanse is not a random void. The observable universe is a highly ordered, deterministic system, driven entirely by precise initial thresholds of mass and angular momentum. 5 to 6 billion years ago, large, extremely cold clouds of hydrogen and helium, called nebulas, began to accumulate at roughly negative 173 degrees Celsius. Intense gravitational pull forces these gas clouds to contract into dense clumps, forming protostars. As they compress, internal pressure drives the core temperature up to 10 million degrees Celsius. At that exact threshold, nuclear fusion ignites. 4 hydrogen nuclei collide to form a single helium nucleus, releasing a massive burst of heat and light. The ultimate fate of that burning star is determined by a strict mathematical boundary known as the Chandrasekhar limit, set at exactly 1.44 times the mass of our own Sun. This flowchart maps the thermodynamic pathways of stellar evolution. For low and medium mass stars below the Chandrasekhar limit, hydrogen exhaustion causes the core to shrink while the outer envelope expands, turning the star into a red giant. Eventually, the outer shell burns away, leaving behind a highly compressed, glowing core known as a white dwarf. Stars that exceed 1.44 solar masses carry enough residual helium in their cores to sustain a secondary fusion chain. This immense internal pressure eventually blows the outer envelope apart in a violent supernova explosion. The remnant of that explosion follows one of 2 final paths. If the mass sits between 1.44 and 3 times that of our Sun, it compresses into an ultra-dense neutron star. If it exceeds 3 solar masses, gravity overcomes all outward atomic pressure, collapsing the core into a black hole. From the exact moment of nebular condensation, a star's entire sequence of birth, expansion, and catastrophic death is mathematically locked by its initial mass. To classify the matter captured by our own star, the International Astronomical Union applies 3 strict criteria to define a planet. It must orbit the Sun, it must possess sufficient mass to achieve a round shake via hydrostatic equilibrium, and it must hold enough gravitational dominance to clear its orbital neighborhood of other debris. Pluto orbits the Sun and is spherical, but it lacks the gravitational mass required to sweep its orbit clean. That specific mechanical failure is the reason it was reclassified as a dwarf planet. This data model illustrates the structural divide of the solar system, starting with the terrestrial group. Mercury, Venus, Earth, and Mars are highly dense, compact rocky bodies. They lack ring systems entirely, and together they possess only 3 moons. The outer Jovian planets, Jupiter, Saturn, Uranus, and Neptune, exhibit the exact opposite parameters. They are low-density giants composed almost entirely of hydrogen and helium gas. They all possess significant magnetic fields, myriad satellite moons, and complex ring systems made of icy debris. These massive Jovian systems generate extreme satellite environments. Jupiter's moon Io is highly volcanic due to intense tidal friction, while Saturn's moon Titan is massive enough to retain a dense, complex atmosphere. Volatile primordial matter also moves through these orbits. As icy comets approach the Sun, the heat sublimates their ice into gas. High-speed solar wind catches this material, forcing the comet's resulting tail to point directly away from the Sun at all times. Heavy, rocky debris forms asteroids. When their trajectories intersect with terrestrial orbits, the kinetic impacts leave massive geographic scars. The Lonar Lake in Maharashtra is a deep crater carved by exactly this type of collision. The solar accretion disk acted as a massive thermodynamic centrifuge. It trapped dense heavy metals close to the core to form solid planets, while driving volatile gases outward to construct the Jovian giants. Earth's localized angular momentum was defined 4.4 billion years ago. The most widely accepted mechanism, the giant impact theory, outlines a collision between the early Earth and a Mars-sized body. The impact blasted a massive volume of debris into space, which eventually coalesced into our own moon. Our planet operates on two continuous mechanical movements. Rotation is the daily turn on its axis, producing alternating day and night and defining our longitudinal time zones. Revolution is the 365-day elliptical orbit around the Sun. This 3D model maps Earth's rotational axis against its orbital path. The axis maintains a fixed 23.5-degree tilt. It is this specific geometric angle, rather than Earth's proximity to the Sun, that dictates the global sequence of the seasons. During the June and December solstices, the axis points one hemisphere directly toward the Sun, placing the solar radiation completely overhead at either the Tropic of Cancer or Capricorn. Halfway through the orbit, during the equinoxes, the axis aligns parallel to the Sun, centering the light over the equator and resulting in perfectly equal hours of day and night. Because the Moon orbits the Earth, its path occasionally intersects the direct line between Earth and the Sun. When the alignment is exact, the Moon visually blocks the solar disk, revealing only the thin, hot gases of the Sun's outer corona during a total solar eclipse. This diagram illustrates the shadow geometry of a lunar eclipse. As the Moon moves behind the Earth, it first enters the penumbra, the outer cone of partial shadow. A total eclipse only occurs when the Moon passes entirely into the umbra, the deepest, darkest center of Earth's shadow. The passage of our days, the shift of our global climate, and the casting of planetary shadows are all direct, observable results of intersecting orbital planes and conserved angular momentum. The mechanics of our solar system represent an unbroken chain of physical causality. The gravitational sorting of our rocky planets and gas giants is a direct extension of an expansion sequence that started 13.7 billion years ago. The nuclear furnaces that illuminate the galaxy operate strictly on mathematical mass thresholds. A fraction of a solar mass dictates whether a star will shrink quietly into a white dwarf or detonate violently across the cosmos. Down to the surface of our own world, the distribution of atmospheric heat and the precision of celestial eclipses execute flawlessly based on rigid, intersecting geometric angles. The universe is completely devoid of randomness. It is a perfectly ordered, mathematically predictable engine, running continually on the ancient physics of a collapsed nebula.